Welcome to Talk Tensors.
Glad to be here for another deep dive.
Okay, let's unpack this. I want you to imagine, if you will, a photograph.
All right, I'm picturing it.
You are standing on a dock, looking out at the water on a bright, perfectly clear, sunny day. And out in the middle of the bay is a sailboat.
Sounds nice.
Yeah.
And I'm guessing this is a really high resolution image, right?
Exactly. It's a massive, brilliant photograph. So you have this giant white sail completely dominating the frame, stretching from the top left corner all the way down to the wooden hull.
Right, a huge visual anchor.
But right there on the deck of the boat, you also have these tiny, intricate details.
Like what?
Like there are people sitting there. Maybe someone is wearing a small, bright orange life jacket. Maybe a seagull is resting on the railing.
Okay, so you've got massive scale differences.
Exactly. Now, as a human being, you look at that photo and your brain just effortlessly processes both the giant sweeping canvas of the sail and that tiny bright orange life jacket in the exact same fraction of a millisecond.
Yeah, you don't even think about it.
Right. You don't have to squint. You don't have to mentally zoom in and out. Your visual cortex handles the massive variance in scale completely flawlessly.
But for an artificial intelligence, that is a totally different story.
Exactly. For a computer vision system, that difference in scale is an absolute nightmare.
It really is. I mean, historically, it's been one of the hardest problems to solve.
So the mission of our deep dive today is answering this. How does an artificial neural network recognize both the giant sail and the tiny life jacket with the exact same level of accuracy?
And crucially, how does it do that without requiring so much computational power that it just, grinds your hardware to a complete halt?
Precisely. We are looking at a classic, seminal piece of research today that completely changed the trajectory of computer vision, the Feature Pyramid Network, or FPN, from the researchers at Facebook AI Research and Cornell.
Yeah, it's an absolute landmark paper.
So before we get into the math, it is incredibly important to establish the context of the era when this paper was published.
Right, which was around late 2016, early 2017.
What was it actually like to be working in computer vision back then?
Honestly, it was frustrating. You were essentially forced into one of two very frustrating camps.
What was the first camp?
On one side, you had the fast, modern, single-scale networks. These were models that they looked at an image at its original resolution just once and processed it.
Like faster RCNN.
Exactly. They were fast enough to be practical, but they were notoriously embarrassingly bad at spotting small objects.
So they would see the sail, but the life jacket essentially just didn't exist to them.
Right. It's just background noise to the network.
And what was the alternative camp? What if you absolutely needed an AI that could find that tiny life jacket?
Then you had to use brute force. The alternative was heavily engineered architectures that relied on what we call featurized image pyramids.
And those were better at small objects.
They were incredibly accurate across all different sizes, but they were computationally brutal.
Because they were processing so much data.
Yeah, I mean, they ate memory and processing power at a rate that made them completely unviable for anything requiring real-time speeds.
Like autonomous driving or live video analysis.
Exactly. It was the ultimate engineering bottleneck, speed versus scale.
So you are a researcher in 2016, and you have to make a painful choice. Do you want your model to be fast, or do you want it to actually see the small stuff?
And you simply couldn't have both. It was an either-or situation.
Which brings us to the core thesis of this paper. And this research fundamentally shattered that dichotomy, didn't it?
It absolutely did. The researchers proved that you could exploit the inherent multi-scale pyramidal hierarchy that already exists naturally inside deep convolutional networks.
And by doing that?
By doing so, you can build high-level semantic feature maps at all scales. And the best part is, you can achieve this at essentially zero extra computational cost.
Which, that sounds like magic. Getting something for nothing in computer science usually means someone is hiding the true cost.
Yeah, it sounds too good to be true.
To understand how they actually achieved this, we need to really understand the depth of the problem they were trying to solve.
We have to go back to those featurized image pyramids I mentioned.
Right. Before deep learning completely took over, in the sort of dark ages of hand-engineered features, why was scale such a massive hurdle?
Well, to really grasp this, we have to look at how computer vision worked before neural networks learned to extract features on their own.
Back when human engineers had to manually write the rules for what an edge or a shape looked like.
Exactly. We relied on hand-engineered algorithms. Two of the most famous ones were SIF, which stands for Scale Invariant Feature Transform, and HOG,
HOG, the histogram of oriented gradients.
Right. Let's talk about HOG because it really illustrates the problem perfectly.
Let's break that down for the listener. What is a computer actually doing when it runs a histogram of oriented gradients? It sounds like it's just counting angles.
That's essentially what it is, yeah. I mean, an image to a computer is just a grid of pixel intensity values, right?
Just raw numbers representing light and color.
Exactly. So HOG works by looking at small blocks of those pixels and calculating the gradients.
And a gradient is just the direction in which the image is getting darker or lighter.
Right. If you have a dark pixel next to a light pixel, you have an edge. HOG calculates the angle of that edge and creates a histogram.
Like a tally chart.
Yeah, a tally of which directions the edges are pointing in that specific little block of pixels.
Okay, so if I'm looking at the mast of our sailboat, HOG is going to tally up a massive number of vertical gradients.
Because the mast is this stark vertical line against the sky.
Exactly. And by tallying up all these gradients across the whole image, the computer builds a sort of crude wireframe understanding of the shapes.
Right. It knows a mast is a collection of vertical gradients, and a life jacket might be a specific circular cluster of gradients.
But there's a fatal flaw here, right?
A massive one. These systems are incredibly rigid regarding size.
Because they're just dumb counting machines at the end of the day.
Yeah. If your algorithm is tuned to recognize a life jacket that takes up a 50 by 50 pixel block, and suddenly the life jacket in the image is only 10 by 10 pixels.
Because the boat is further away in the photo.
Exactly. Then the gradients completely change. The 10 by 10 pixel life jacket doesn't produce the same histogram.
The computer is just totally blind to it.
Completely blind. It's looking for a specific pattern at a specific size.
If the pattern shrinks, the lines blur together, the gradients shift, and that mathematical signature is just lost.
So researchers had to fix that. But how? If the algorithm can only find a 50 by 50 pixel life jacket, how do you find the 10 by 10 one?
You literally have to physically change the size of the image to match the algorithm.
Yes. And that is exactly what an image pyramid is.
That sounds so tedious. It was.
You take your original high-resolution photograph, you run your HOG algorithm over the whole thing.
Okay.
Then you resize the image, you shrink it down by a certain percentage.
Yeah.
You run the algorithm again.
Over the entire shrunk image.
Yep. Then you shrink it again. You run it again. You are literally building a pyramid of images from the massive high-resolution original at the base to a tiny postage stamp-sized version at the top.
I am trying to visualize the sheer amount of redundant work happening here. It's like physically printing out 10 different sized copies of a photograph.
That's a great analogy.
You print a massive poster-sized version, lay it on a giant table, and scan every single inch of it with a magnifying glass, just looking for your lost keys, or, in our case, the life jacket.
And then you print a slightly smaller poster and scan the whole thing again.
You just keep printing smaller and smaller versions until the tiny 10 by 10 life jacket is mathematically scaled up relative to your magnifying glass to look like a 50 by 50 life jacket.
It works, but it is agonizingly slow.
Agonizing is the perfect word. How densely were they actually doing this back then?
In the era of hand-engineered features, they were doing this incredibly densely. To ensure they didn't miss anything, researchers would create up to 10 different scales per octave.
Wait, an octave? Like in music?
Similar concept of halving or doubling. An octave in this context means having the resolution of the image.
Okay, so between the original image and an image exactly half its size, they would generate 10 intermediate resized versions.
Yes, and run the feature extraction on every single one of them.
That is insane. But I guess because SIFT and HOG were just doing basic math, just counting gradients and edges, they were computationally light enough that standard CPUs could sort of handle it.
Right. It was slow, but it wasn't mathematically impossible for the hardware of the time.
But then the tectonic plates of the industry shifted.
We entered the deep learning revolution.
The era of hand-engineered features was just completely wiped out.
Replaced by deep convolutional neural networks, or convets, models like Overfeet, AlexNet, and eventually the RCNN family.
Let's establish why convets killed the old methods. A convnet isn't just looking at gradients, it's learning its own features.
Exactly. It uses filters that slide across the image, recognizing simple edges at first, but then it combines those edges into textures.
And textures into shapes.
And shapes into complex objects. It builds a hierarchical understanding of the image.
And crucially, convnets are actually inherently somewhat robust to scale variance, right?
They are, because they use sliding windows and pooling layers, which basically condense the information as it moves deeper into the network. A convnet has a little bit of flexibility.
You can recognize a dog if it's a bit larger or a bit smaller without needing you to feed it a completely resized image.
Because of this newfound robustness, the designers of the next generation of detection systems made a calculated gamble.
We're talking about systems like fast RCNN and faster RCNN.
Yes, they decided to throw the image pyramid completely out the window.
Just abandon it entirely.
They opted to compute their features on a single input scale. You feed the image once at one size and let the deep connet do its magic.
I can completely see the logic there. You have this massive, powerful neural network. It's computationally heavy on its own.
Very heavy.
If you try to run a deep ComNet on an image pyramid, running the entire 50-layer or 100-layer neural network on the poster size, then the slightly smaller size, then the medium size.
Your GPU would just melt.
Exactly. The hardware just couldn't do it.
The math backs you up. Researchers at the time tried it. Running a deep network independently on multiple scales of an image pyramid increased the inference time by roughly 400%.
400%?
Yeah. A model that might have run at 5 frames per second on a video feed was suddenly taking a full second just to process a single frame.
Making it totally useless for real-time applications.
Completely useless. But there was an even bigger problem than speed.
There's a fundamental limitation with how neural networks are trained versus how they are tested.
Exactly. Deep ComNets require huge amounts of GPU memory to train.
Because when you are training a model, you aren't just passing an image through it.
Right. You are storing the activations of every single layer so you can run backpropagation and update the weights.
You simply could not fit a full multi-scale image pyramid into the GPU memory during training.
The hardware at the time just couldn't handle it. The VRAM would max out instantly.
So researchers were forced into a terrible compromise.
They would train the network on single-scale images because that's all the memory could handle.
But then in the real world, during testing or deployment, they would try to run the network on an image pyramid to catch the small objects.
Which breaks the fundamental golden rule of machine learning.
Train and test consistency.
You are asking the model to perform in a deployment environment that looks vastly different from its training environment.
The results had to be inconsistent.
Inconsistent and inefficient, so the field rallies around the single-scale convent.
Faster RCNN becomes the reigning champion. It only looks at the image once. It is incredibly fast.
And it is highly accurate for medium and large objects.
It can find the giant white sail perfectly.
But because we threw away the image pyramid, we are back to square one with the tiny objects.
If the life jacket doesn't take up a substantial chunk of the frame, the single-scale ConNet just completely overlooks it. It is blind to the small stuff.
Which naturally led researchers to ask, is there a way to get the benefits of an image pyramid without actually building one?
And that brings us to the internal structure of a convent itself. I'm putting myself in the shoes of someone following the field at that time. I'm thinking, wait, a deep neural network already builds a pyramid internally, doesn't it?
It does. As an image passes through the layers of a convent, the spatial resolution is intentionally reduced.
It shrinks the spatial dimensions while increasing the channel depth.
Right.
But wait, didn't systems like SSD, the single-shot detector, try to fix this by looking at different layers of the network?
They did, and it is a very astute point to bring up SSD. SSD was one of the first major successful attempts to use the convent's internal hierarchy as a sort of built-in pyramid.
The designers of SSD realized that the network naturally creates a series of feature maps that get progressively smaller in spatial resolution.
Let's visualize that internal pyramid for a second. The first layer looks at the original high-resolution image.
And it outputs a map that is maybe half the size.
Then the next major block outputs a map a quarter of the size.
The deepest layers output a map that is physically tiny in terms of spatial dimensions, but incredibly deep in terms of feature channels.
SSD tried to say, let's attach a prediction head to each of these different intermediate layers.
We'll look for small things on the early high-resolution layers, and we'll look for massive things on the deep low-resolution layers.
That was the theory. But here is the critical flaw, and the reason SSD ultimately failed to solve the small object problem.
What was it?
SSD avoided the low-level high-resolution layers entirely.
Wait, why? If you are looking for a tiny life jacket, you need high resolution. Why would they intentionally skip the only layers that have the spatial precision to see it?
Because of what we call the semantic gap.
Okay, unpack the semantic gap for me.
The designers of SSD understood a fundamental truth about ComNets. The early high-resolution layers have very weak semantic meaning.
Think back to our HOG discussion, right?
Exactly. The first layer of a connet is essentially just finding raw edges, corners, and color gradients.
It doesn't possess the concept of a life jacket or a sailboat.
It just sees a cluster of orange pixels bordered by dark pixels. It's like an infant seeing shapes but not knowing what the objects actually are.
So if you ask an edge detector to classify a complex object, it's just going to output garbage.
Because it hasn't built up the vocabulary yet. It's not until you get much deeper into the network after the data has been pooled and convolved multiple times that the network builds a strong semantic understanding.
The deep layers know what a dog, a person, or a boat looks like.
But because of the pooling, those deep layers have incredibly coarse spatial resolution.
The image has been shrunk so much that the tiny life jacket has literally been pulled out of existence.
It was averaged into the pixels of the deck and just disappeared.
This is a brutal paradox.
It really is. By skipping the early layers, SSD threw the baby out with the bathwater.
They missed the exact high-resolution layers you absolutely need to accurately locate tiny objects, because those layers weren't smart enough yet.
But by the time the layers get smart enough, the resolution is too blurry to find the tiny objects.
This raises an important question. How do you get high resolution and strong semantics at the exact same time?
That defines the core problem the FAIR researchers had to solve. You need the sharpness of the early layers and the intelligence of the deep layers, coexisting in the exact same mathematical space.
If the memory wall stops us from using literal image pyramids, and the semantic gap stops us from using the internal layers of SSD, we are backed into a corner. How did they actually build this feature pyramid network?
The architecture they designed relies on three heavily integrated components. A bottom-up pathway, the top-down pathway, and the lateral connections. It's a system of routing information backward through the network.
But let's start with the foundation, the bottom-up pathway. That is essentially just the normal forward-moving operation of a standard deep learning model, right?
Exactly. For their experiments, the authors primarily used ResNet as their backbone architecture.
A backbone is just the core feature extractor.
Right. As the raw image passes forward through the ResNet backbone, the network processes it in stages.
And at the end of each major stage, the spatial resolution of the feature map is cut in half.
Let's define the terminology they use in the paper because it's crucial for understanding the rest of the architecture.
Okay.
They refer to the output of the last residual block in each of these stages using the letter C. So we have C2, C3, C4, and C5.
What do those numbers actually represent?
The numbers correspond to the scaling step, specifically related to the pixel stride relative to the original input image.
So when we talk about a stride of 2, it means the dimensions are halved. A stride of 4 means the dimensions are quartered.
Correct. So let's trace the image. It enters the network. By the time it finishes the first major block, it reaches C2.
C2 has a stride of 4. So if our original image was 1,000 by 1,000 pixels, the C2 feature map is 250 by 250.
Exactly. As we go deeper, C3 has a stride of 8. C4 has a stride of 16.
And finally, C5, the deepest layer in our reference set, has a stride of 32.
C5 is extremely low resolution. That 1,000 by 1,000 image is now represented by a tiny 31 by 31 grid.
But because it has passed through dozens of convolutional layers, C5 is semantically brilliant.
It contains the highest level, most sophisticated understanding of what objects are in the image.
Now, I'm noticing a missing number. What happened to C1, the very first layer of the network? Why is it excluded from this architecture?
It comes down to strict memory economics. C1 has a massive spatial resolution.
It's usually only half the size of the original image, right?
Yeah. So if you try to store all the feature channels for a map that large and include it in your pyramid processing, the memory footprint absolutely explodes.
So the computational cost outweighs any marginal benefit you might get from that ultrafine resolution.
Pragmatically, they drop C1 and start building the pyramid from C2.
Okay, so we have our foundation, the bottom-up pyramid. The top of this pyramid is C5. It is very smart, but spatially, it's very blurry.
Right.
The bottom of our functional pyramid is C2. It is very sharp, very high resolution, but it's not very smart. It just sees edges.
And this is exactly where SSD got stuck.
So how do we make C2 smart?
We initiate the second component, the top-down pathway.
The top-down pathway.
We take the intelligence from the top and physically force it down the pyramid.
This is the hallucination phase. I want to spend some time on exactly how this mechanism works because honestly, it sounds impossible.
It does sound a bit counterintuitive at first.
We take that C5 layer, the tiny 31 by 31 grid that knows exactly what a sailboat is, and we upsample it.
We literally stretch it out to be twice as big so its spatial dimensions match the C4 layer below it.
How does an algorithm stretch a grid of numbers without destroying the data?
They chose the simplest possible mathematical method: nearest neighbor upsampling.
Nearest neighbor.
When you want to double the size of a matrix, you don't calculate complex gradients or try to interpolate new values. You simply duplicate the existing pixels.
Okay, so if you have a single pixel in C5 with a value of, say, 0.8,
and you upsample it by a factor of 2, that single pixel becomes a 2x2 block of 4 pixels.
and every single one of them has the exact same value of 0.8.
Every single one.
I am picturing an old retro 8-bit video game. When you take a tiny sprite character and stretch it to fill a modern TV screen, it doesn't suddenly get more detailed.
No, it just gets blocky.
Every single pixel turns into a giant square of the exact same color.
That is a perfect visualization. Nearest neighbor upsampling creates severe aliasing effects. It makes the feature map blocky and spatially jagged.
But remember, we aren't trying to create a pretty picture here.
We are trying to propagate semantic meaning. By duplicating those values, we take the deep understanding of C5 and expand its spatial footprint.
But wait, I have to push back here. If you just stretch a blurry semantic map, it's still blurry.
Well, yes.
It's just a larger blurry map. The spatial locations are completely imprecise.
That is true.
If C5 knows there is a life jacket somewhere in the bottom right quadrant, upsampling it doesn't suddenly tell you exactly which pixels form the boundary of the life jacket. You haven't solved the spatial problem.
You are absolutely correct. Upsampling alone is useless for precision detection.
So what's the missing piece?
That is why the top-down pathway cannot exist in a vacuum. It must be fused with the high-resolution data from the bottom-up pathway.
Ah.
This is the third and most critical component: the lateral connections.
This is the magic glue.
Exactly.
We take that upsampled, blocky, but highly intelligent map coming down from C5, and we want to merge it with the C4 map.
Which is sharp, high resolution, but lacks that deep intelligence.
We want to smash them together. But from a matrix math perspective, I am struggling to see how this works. The channel dimensions are completely mismatched.
They are drastically mismatched. Deep convolutional networks operate like funnels. As the spatial dimensions shrink, the network compensates by increasing the number of feature channels.
The depth of the matrix.
Right. C2, being early in the network, might only have 256 feature channels. But C5, at the very end, has been expanded to 2048 channels.
You cannot mathematically perform an element-wise addition on a matrix with 256 layers and a matrix with 2048 layers. It breaks the rules of linear algebra.
You can't. So how do you align them? How do you force a 2048 channel map and a 256 channel map to speak the same language so they can be merged?
That's the question.
You apply a one-by-one convolution.
Oh, the one-by-one convolution. This is one of the most elegant tools in deep learning.
It really is. Before they merge the maps, they take the bottom-up feature map, let's say C4, and pass it through a one-by-one convolutional layer.
Let's demystify the one-by-one convolution for the listener, because it's a term thrown around in almost every modern paper, but its mechanism is often really misunderstood.
It sounds contradictory, doesn't it?
It does. A convolution usually looks at a 3x3 or 5x5 grid of pixels to find spatial patterns. How can a one-by-one convolution find a pattern if it's only looking at a single pixel?
The secret is that it doesn't look for spatial patterns at all. A one-by-one convolution ignores the width and height of the image entirely. It strictly operates on the depth, the feature channels.
Imagine looking straight down through a single pixel coordinate all the way through the 2048 channels of the matrix.
Right. A one-by-one convolution acts like a blender. It takes the values from all 2048 channels at that specific pixel location, assigns a learned weight to each one, mixes them together, and outputs a brand new value into a predetermined number of channels.
So it's a channel compressor.
Exactly. The FAIR team decided to fix the channel dimension for their entire pyramid. Let's call this fixed dimension D.
And they set D to exactly 256 channels.
Yes. They apply a one-by-one convolution to every single bottom-up map. C2, C3, C4, C5. Regardless of how many channels those maps originally had, the one-by-one convolution acts as a bottleneck, compressing or transforming them all down to exactly 256 channels.
Okay, the pieces are falling into place for me now. We have our upsampled top-down map, which is 256 channels deep.
Right.
We have our high-resolution bottom-up map, which has just been run through the one-by-one blender and is now also exactly 256 channels deep.
They are spatially identical. They're dimensionally identical.
Yeah, what?
Now, they undergo a simple element-wise addition.
Simple addition.
For every single spatial coordinate and for every single channel, the network just adds the numerical value from the top-down map to the numerical value of the bottom-up map.
That is stunningly simple. There are no complex, non-linear mathematical gating mechanisms.
None.
There's no attention mechanism deciding which map to trust more. It just straight up adds the numbers together.
What's fascinating here is the simplicity. The authors intentionally avoided complex nonlinearities for the merging process.
Why?
By using simple addition, the computational overhead of building this entire top-down pyramid is practically invisible. It requires almost zero extra processing power compared to the heavy lifting the ResNet backbone is already doing.
We aren't quite finished, though, are we? We merged the sharp bottom-up map with the blocky, upsampled top-down map. But we noted earlier that nearest neighbor upsampling causes terrible aliasing.
The 8-bit video game effect?
Exactly. If we just add those 8-bit blocks to our sharp map, wouldn't it corrupt the spatial precision?
It would. So there is one final cleanup step. After the element-wise addition is complete, the network applies a standard 3x3 convolution to the newly merged feature map.
What is the mechanical purpose of that 3x3 pass?
It acts as a spatial smoothing filter. A 3x3 convolution looks at a small neighborhood of pixels. It takes those harsh, blocky edges created by the nearest neighbor upsampling and smooths them out,
blending the rich semantic data seamlessly into the precise spatial boundaries provided by the bottom-up map.
Exactly. The output of this 3x3 smoothing convolution is your final finished feature map for that level of the pyramid.
And to distinguish these newly minted hybrid maps from the original C maps, the authors label them P for pyramid.
So C2 becomes P2.
C3 becomes P3, and so on. We now have a completed feature pyramid network. P2, P3, P4, and P5. Let's just pause and synthesize what this actually means fundamentally.
It's worth taking a step back to appreciate.
Look at P2. It sits at the bottom of the pyramid. It has the immense spatial resolution of the original C2 layer, right? It can easily draw a tight bounding box around a tiny life jacket.
Yes, the spatial precision is intact.
But because of the top-down pathway, it has received a direct injection of pure semantic intelligence cascading all the way down from C5.
P2 is no longer just a dumb edge detector.
It knows what a life jacket is, and it knows exactly where it is.
They solved the dilemma. You have high spatial resolution and strong high-level semantics simultaneously across every single scale of the image.
It is a beautiful piece of theoretical architecture. But as we know, an architecture is just a theory on a whiteboard until it is plugged into a working system and tested against the chaos of real-world data.
Theory only goes so far.
The FR researchers had to prove this actually functioned, so they integrated FPN into the undisputed object detection champion of the time.
Faster RCNN.
Integrating FPN into faster RCNN wasn't just a plug-and-play operation, though, was it?
Not at all. Yeah. Faster RCNN is actually a complex two-part system, and both parts had to be fundamentally rewired to understand a multi-level pyramid.
Let's break down that rewiring, starting with the first half of the system, the Region Proposal Network, or RPN. What is the actual mechanical job of the RPN?
The RPN acts as the eyes of the detector. Its only job is to slide a window across the feature map and find areas of interest.
So it doesn't care what an object is?
No, it doesn't know a boat from a bird. It just points at a cluster of pixels and says, hey, there's a high probability that something is inside this specific bounding box. Pay attention here.
We call these class-agnostic object proposals.
Exactly.
And how did the original faster RCNN do this? It only had one single feature map to look at.
Because it only had one map, it had to cast a very wide net from every single location. As the sliding window moved across the map, it dropped anchors.
Think of an anchor as a hypothetical bounding box.
Right. At every single stop, the original RPN would throw out a tiny anchor box, a medium anchor box, and a massive anchor box, all centered on the exact same pixel, hoping that one of those boxes happened to perfectly wrap around whatever object might be there.
It's essentially guessing sizes because it only has one perspective.
But with FPN, the paradigm completely changes. We don't have one map. We have a 5-level pyramid of varying resolutions.
So we don't need to throw out multi-scale anchors on a single level anymore. We can specialize.
Exactly. The anchors are now assigned specifically by size to the different pyramid levels. It is a strict, rules-based sorting system.
How does the sorting work?
The smallest anchors, which are predefined as 32 by 32 pixel areas, are assigned exclusively to the highest resolution level, P2.
If you are looking for something tiny, you look on the sharpest map.
Which makes perfect logical sense. Moving up, the 64 pixel squared anchors are assigned to P3, 128 pixels squared to P4, 256 pixels squared to P5.
And to handle truly massive objects that take up the entire frame?
They actually introduce a brand new level, P6, which is just a pooled version of P5, specifically for massive 512 pixel squared anchors.
So the workload is perfectly distributed, but here is the detail in the paper that I consider the absolute aha moment of the entire architecture.
I think I know which one you're going to say.
The researchers note that the parameters, the actual learned mathematical weights of the RPN prediction heads, are completely shared across all levels of the feature pyramid.
It is a profound detail.
Explain that for me.
The RPN uses a small subnetwork, a head, to look at an anchor and decide if it contains an object. In FPN, they don't train a different head for P2 and a different head for P5.
They use the exact same head with the exact same weights applied to every single level of the pyramid.
Yes.
I want to make sure you listening grasp why this is so critical. If the exact same mathematical formula can successfully detect a tiny life jacket on P2 and then turn around and use the exact same math to successfully detect a massive sail on P6, what does that prove about the pyramid?
It mathematically proves that all levels of the pyramid share similar semantic strength.
It proves the top-down hallucination worked.
The network doesn't need to learn a different set of rules for small objects versus large objects. Because the pyramid naturally scales the spatial dimensions while holding the semantic depth constant, a life jacket on P2 looks mathematically identical to the AI as a giant sail on P6.
True scale invariance has been achieved.
It's incredibly elegant.
Okay, so the RPN is sliding across all these levels, dropping its specialized anchors, and generating thousands of proposals.
Regions of interest or ROIs.
Now, we have to pass those ROIs to the second half of the faster RCNN system, the actual detector head.
The detector has to look inside those proposed boxes and classify them.
It has to say, yes, this box contains a person, and this box contains a seagull.
But immediately we run into a massive logistical problem.
Right. In the old system, the detector just looked at the one single feature map.
Now, we have 5 different P levels. If the RPN hands the detector a random bounding box, how does the network know which level of the pyramid it should extract the features from to classify it?
It requires a dynamic routing mechanism.
The network needs a way to instantly sort the rows. To do this, the FAIR team adapted an equation originally used in traditional old-school image pyramids.
The equation assigns a target pyramid level, which we will call Teilhardal, based entirely on the mathematical area of the proposed roi.
It involves taking the floor of 4 plus the base 2 logarithm of the square root of the roi's width times height, divided by 224.
Reading raw formulas on audio is a recipe for disaster.
True.
Let's translate this math into a physical analogy for you. Focus on the behavior of this equation. How does it act?
Think of the equation as a highly efficient sorting hat. It is anchored by a baseline constant, the number 224.
224 by 224 pixels is the canonical standard image size used for pre-training models on the massive ImageNet dataset.
Exactly. The sorting hat compares the size of every single proposed object against that standard 224 baseline.
Let's run a test case. Say the RPN proposes a bounding box that is exactly 224 by 224 pixels.
The sorting hat does its math, and the result is the baseline level. 4. The network routes that object straight to level P4 for classification.
Okay, that's the baseline. But what if the object is significantly smaller? What if it's our tiny life jacket?
This is where the logarithm comes into play. A base 2 logarithm essentially measures how many times you have to have a number.
So if your proposed object is only 112 by 112 pixels, exactly half the size of the 224 baseline.
The logarithm registers that single halving step. The sorting hat takes the baseline of 4, subtracts 1, and assigns the object to level 3. The object is routed to P3.
And if the object is halved again, if it's only 56 by 56 pixels.
The sorting hat subtracts another level, it drops the object down to P2. The mechanism is perfectly proportional.
For every time the object cuts its size in half, the equation automatically drops it one step lower on the pyramid to a finer resolution layer to get a better look.
And conversely, if the object is massive, like a 448 by 448 pixel sail, it adds a level and pushes it up to the coarse resolution of P5.
It is an incredibly efficient self-sorting mechanism. It guarantees that the classifier head is always looking at the object at the optimal resolution.
And just like the RPN, the detector head shares its parameters across all levels.
So we have built the pyramid, we have integrated it with RPN and faster RCNN using specialized anchors and a mathematical sorting hat.
The architecture is logically sound.
But logic doesn't always translate to performance. We need to look at the benchmark results.
They tested this entirely novel system on the COCO dataset, which is notoriously difficult because it features highly complex scenes with tiny occluded objects.
What happened when they ran the numbers?
The result triggered a paradigm shift in the field.
Let's look strictly at the RPN first, its raw ability to just find proposals, regardless of what they are. This is measured by a metric called average recall, or AR.
Adding the feature pyramid network to the baseline, faster RCNN, increased the average recall for bounding box proposals by a massive 8.0 points.
An 8-point jump in overall average recall is a massive leap for a single architectural tweak.
It is.
But that is just the overall average. Here's where it gets really interesting. If you isolate the data set and look strictly at the performance on the small objects in COCO, the tiny life jackets and seagulls, what was the impact?
This is where the paper cemented its legacy. For small objects, the average recall was boosted by a staggering 12.9 points.
Wow.
FPN didn't just improve the detection of small objects, it completely eradicated the small object blindness that had been plaguing single-scale convent nets for years.
It proved that the high-resolution early layers, when injected with top-down semantics, were fully capable of finding the tiniest details.
And that's just finding the boxes.
Right. What about the full detection pipeline? When the fast RCNN head actually had to classify the objects, how did FPN compare to the heavyweights of the era?
On the full COCO detection benchmark, FPN achieved state-of-the-art single-model results.
It didn't just beat the baselines, did it?
It outright destroyed the heavily engineered competition winners from 2015 and 2016.
We're talking about incredibly complex, resource-heavy systems like faster RCNN+++ and GRMI, which utilized massive ensembles of different models, complex iterative localization, and all sorts of computational tricks to scrape out a few extra percentage points.
And FPN beat them with a single, elegant model. As the authors proudly stated in the text, they achieved state-of-the-art without bells and whistles.
It is the academic equivalent of a mic drop.
Okay.
But I am not going to just take their word for it. I want to play devil's advocate here.
Go for it.
This architecture has a lot of moving parts. We've got upsampling, one-by-one bottlenecks, element-wise additions, smoothing convolutions. How do we know that the top-down pathway and those lateral connections actually did the heavy lifting?
Well,
Maybe ResNet is just so powerful that simply attaching predictors to the bottom-up pyramid would have been enough.
this is why rigorous papers include ablation studies.
An ablation study is where you systematically sever parts of your own model to prove their worth.
The FAIR authors were highly methodical here. First, they tackled your exact hypothetical. They removed the top-down pathway entirely.
Okay, so they just took the standard bottom-up CondNet, attached predictors to C2, C3, C4, and C5, and ran the benchmark.
Yep.
What happened?
The performance plummeted right back to baseline levels. It failed miserably.
Why? I want the mechanical reason for the failure.
Because of the semantic gaps between the layers that we discussed earlier.
C2 has immense spatial resolution, but very low-level semantics.
When you sever the top-down pathway, you stop the flow of intelligence from C5. C2 goes back to just being a dumb edge detector.
When the detector head looks at C2 and tries to classify a bounding box, it has no idea what it's looking at. It's guessing.
Exactly. The top-down hallucination is absolutely required to give those lower levels the vocabulary they need to classify objects.
Okay, the top-down pathway is validated, but what about the lateral connections?
They ablated that as well.
What if we just take C5, upsample it a bunch of times to build a high-resolution top-down pyramid, and make predictions exclusively off that without ever merging the sharp bottom-up data via the one-by-one convolutions?
They severed the lateral connections, and the result was catastrophic. The average recall score dropped by a full 10 points.
10 points. That proves the fusion is vital. But again, mechanically, why does it fail so hard?
It comes back to the aliasing effect of nearest neighbor upsampling. When you upsample a coarse 31 by 31 map repeatedly to get it up to 250 by 250, you severely degrade the spatial precision.
The semantic information survives. The model might know exactly what the object is.
But because the pixels have been duplicated into massive, blocky squares, the bounding box it draws will be incredibly sloppy. It won't tightly wrap the object. It will encompass huge chunks of the background.
The lateral connections are non-negotiable because they inject the crisp, pixel-perfect boundaries of the original image back into the blurry semantic map.
The logic is airtight. The components rely entirely on each other.
But there is one final metric we haven't discussed: speed.
Ah, yes.
Earlier, we established the ultimate trade-off. Image pyramids were accurate, but agonizingly slow. Single-scale networks were fast but blind. FPN is accurate and can see everything. But did it tank the frame rate?
How fast does this massive architecture actually run?
Yeah, what's the FPS?
This might be the most impressive engineering feat of the entire paper. FPN ran at 6 frames per second on a single GPU of that era.
6 frames per second is totally viable for real-world video processing, but I am struggling with the math of the computational load.
It does seem like a lot.
We added an entirely new top-down pathway, we added a half dozen convolution layers, we added merging operations. It seems mathematically impossible for it to run at 6 FPS. Shouldn't it be significantly slower than the single-scale baseline?
You would intuitively think so, but it was actually faster than the single-scale ResNet-based faster RCNN counterpart.
How? Where did they cut the weight?
The secret lies in the classifier head.
Explain.
In the standard single-scale ResNet implementation of faster RCNN, the classification head, the part that actually looks at the row I and makes the final decision, was incredibly heavy. They used the entire conv5 layer of ResNet as the head.
conv5 is a 9-layer deep, massive subnetwork.
And in faster RCNN, you have to run that massive head on every single region proposal. If the RPN finds the 1,000 proposals, you run a 9-layer deep network 1,000 times per image. It's a massive bottleneck.
Ah, I see it. With FPN, we already used conv5.
Exactly. conv5, which we've been calling C5, was already used to build the top of the pyramid. Its computational cost is already baked into the feature extraction phase.
The features have already passed through it.
Therefore, the FAIR team didn't need a massive, heavy classification head anymore. They stripped out the conv5 head and replaced it with a simple, lightweight, multi-layer perceptron, or MLP.
Let's define an MLP in this context. It's just a couple of fully connected layers.
Right. It flattens the feature map into a 1D array of numbers and passes it through 2 simple, dense layers to output a classification. It's mathematically trivial compared to a 9-layer convolutional block.
The time they saved by lightening the detector head massively outweighed the tiny computational cost of the 1x1 lateral connections and the element-wise addition.
FPN wasn't just more accurate, it was a more efficient allocation of computational resources.
A true foundational paper, though, doesn't just solve one highly specific problem, like drawing bounding boxes. A seminal paper introduces a mechanism that becomes a generic tool for the entire field.
And FPN definitely became a generic tool.
Did the FPN architecture extend beyond object detection? Could it be used for other, more complex visual tasks?
It absolutely did, and the authors made sure to prove it in the paper. They explicitly demonstrated FPN's versatility by extending it to the task of instance segmentation.
For you listening, instance segmentation is a much harder task than object detection. Instead of just drawing a rough rectangular box around a sailboat, the AI has to perform pixel-perfect classification.
It has to generate a mask that perfectly outlines the exact irregular shape of the sail, the hull, and the mast, separating those specific pixels from the water and the sky.
At the time, the state-of-the-art systems for generating these masks were models called deep mask and sharp mask.
But they suffered from the exact same problems we've been discussing. To get accurate masks for objects of different sizes, they relied on densely sampled image pyramids.
So they were incredibly slow.
Very slow.
So how did the FAIR team adapt FPN to draw masks? Did they have to invent an entirely new routing mechanism?
The adaptation was almost shockingly simple, proving the robustness of the pyramid. They kept the exact same FPN architecture.
Okay.
But instead of attaching a bounding box head, they attached a small segmentation head on top of each level of the feature pyramid. Specifically, they applied a small 5x5 multi-layer perceptron to the feature maps to predict a 14x14 pixel mask for each region of interest.
But wait, earlier we said the anchors were fixed at specific sizes. 32, 64, 128. What if an object falls perfectly between those scales? What if the life jacket is exactly 48 pixels wide?
That is a great question, and it's a detail the authors accounted for. To handle objects that fell strictly between the pyramid scales, they added a second, slightly larger 7x7 MLP designed specifically to generate masks for those half-octave sizes.
It's an incredibly thorough design. And what did the numbers look like when they ran the segmentation model?
FPN achieved a 48.1 average recall for masks. It outperformed the state-of-the-art deep mask and sharp mask systems by over 8.3 points overall.
And echoing the object detection results, it nearly doubled the accuracy on small object masks.
But the real triumph was the speed. It achieved this massive leap in precision while running at 6 to 7 frames per second.
The older image pyramid methods literally crawled in comparison, taking fractions of a minute per frame.
FPN proved beyond a shadow of a doubt that it was a generic, universal, multi-scale feature extractor.
It's just a masterclass in elegant, efficient engineering, but no paper is perfect, and I always think it's vital to examine the limitations of a study.
Absolutely.
What did the FAIR team leave on the table? What were the blind spots or the explicit limitations acknowledged by the authors themselves?
The authors were exceptionally transparent about their design choices. They explicitly admitted to keeping the connection modules, the one-by-one convolutions, and the simple element-wise addition as mathematically basic as possible.
Right.
They noted in the text that they actually experimented with much more sophisticated nonlinear residual blocks for those lateral connections, and those complex blocks did yield marginally better benchmark results.
So why not publish the model with the complex blocks? In academia, everyone is fighting for that extra 0.5% on the COCO leaderboard. Why intentionally kneecap your own architecture's maximum theoretical performance?
Because they valued clarity and provability over a marginal leaderboard bump. They consciously chose simplicity.
They wanted to prove that the core, fundamental concept routing semantic data top-down and merging it laterally was the sole reason the model worked.
Exactly. If they muddied the waters with highly complex mathematical gating, critics could argue that the complex math was doing the heavy lifting, not the pyramid structure.
That makes a lot of sense.
Furthermore, they noted that their deepest, most powerful model, which used the massive ResNet 101 backbone, wasn't sufficiently trained. They stopped the training on the default schedule.
They openly acknowledged that with more compute time, they likely could have squeezed even more performance out of it.
Yes. They left room for the rest of the computer vision community to optimize it.
They handed the world the blueprint and said, here, you build the skyscraper. And optimize it they did.
The lasting influence of this paper cannot be overstated. FPN became an inescapable foundational building block in computer vision.
Whether you are looking at modern object detection algorithms, complex instance segmentation models like mask RCNN, which came shortly after, or even highly nuanced tasks like human pose estimation and key point tracking, you will find the DNA of FPN.
The fundamental concept of the top-down, laterally connected feature pyramid completely eliminated the need for computational heavy image pyramids in standard applications.
It changed how neural networks process the visual world, which brings us to my absolute favorite segment of the deep dive. We have covered the history, we have meticulously unpacked the math, we've reviewed the benchmarks and the legacy. Now we push the boundaries.
It is time for the novel notions segment. I am ready.
As a strict reminder to you listening, the following research pitches are purely speculative and strictly for entertainment purposes only. This is the part of the show where we take the core mechanisms of the paper we just analyzed.
In this case, the top-down hallucination and the lateral merging.
And we push them to outlandish but logically consistent extremes to see what bizarre new research ideas might fall out. We have two pitches today. Let's hear your first one.
Okay, my pitch is an architecture. I am calling temporal FPN for cognitive video prediction.
Temporal FPN. I like the name.
Throughout this entire deep dive, we have been talking about FPN purely in the spatial dimension. We are moving data across X and Y coordinates on a static 2D photograph.
Right.
But what if we take this exact architectural mechanism and force it into the fourth dimension, time?
What if we build a temporal pyramid network? Okay, I'm tracking the concept, but I need the mechanics. How does a temporal FPN actually work?
Imagine a system processing a live, continuous video feed. The bottom-up pathway isn't just processing the current frame, it is pushing sequential data forward through a predictive temporal model, like an advanced transformer or an LSTM.
Okay, so it's predicting.
Because it's a predictive model, the highest level of this pyramid, the equivalent of our highly semantic C5 layer, isn't just a low-resolution spatial map. It's a highly semantic, low-resolution future state prediction.
Oh, wow.
Is the network mathematically guessing what the scene will mean 1 or 2 seconds from now?
So C5 isn't just the deep features of the present. C5 is literally the hallucinated future.
Yes. And then we apply the FPN top-down pathway. We take that hallucinated semantic future, upsample it, and push it backward in time.
We merge it via lateral one-by-one convolutions with the high-resolution present-moment frames from the bottom-up pathway.
The immediate real-world application for this has to be autonomous driving.
Think about a self-driving car's dash cam. The predictive C5 layer sees a pattern of movement, maybe a cluster of pixels near the edge of a parked car, and its semantic future state predicts that cluster of pixels is a pedestrian who is about to step out into the street.
That is the blurry semantic future. By using the temporal FPN, you force that high-level future context down into the high-resolution immediate layers processing the present frame.
It turns predictive modeling from a separate, detached downstream task into an integrated feature enhancement mechanism for the present moment.
The high-resolution present is actively being informed and altered by the semantic future.
The car could mathematically identify hidden hazards fractions of a second faster than a purely reactionary system because the early layers are preloaded with future context.
Precisely.
That is a phenomenal application of the mechanism. Okay, here's my pitch. Research idea 2. Inverse FPN for generative multi-scale rendering.
Generative rendering, okay. Let's hear it.
We are currently living through a massive explosion in generative AI, Midjourney, DALL-E, Sora. These are mostly driven by sequential diffusion models.
Right, which are amazing but have their drawbacks.
Diffusion models are incredibly powerful, but they take a massive amount of time because they have to denoise an image step by step sequentially.
Yes, step 1, step 2, step 3.
What if we take the FPN pyramid and flip it completely upside down for generation? Instead of detecting objects from an image, we use the pyramid to generate the image from scratch.
I like where this is going. Walk me through the actual matrix mechanism.
You start the generation process at the very top of the pyramid, but you don't start with random static noise. You start with a tiny, dense semantic token map.
This is our C5 equivalent.
It's basically the pure, compressed idea of the scene, say an encoded representation of a sailboat on the water. It has absolutely zero high resolution. It is just pure semantic meaning in a tiny matrix.
Okay, got it.
Then you pass it down an expanding pyramid, you upsample it. But here's the trick. In the original FPN, the lateral connections pull in sharp image data from the bottom-up pass.
Right, but in an inverse FPN, there is no bottom-up pass because there is no image yet.
Exactly. Instead, at every step of the expansion, you use the lateral connections to inject specific mathematical high-frequency noise profiles. You texture the generation.
Oh, it's clever.
The tiny semantic map gives the broad layout. You expand it, inject mid-level noise for the waves and clouds, expand it again, inject fine-grained noise for the texture of the canvas sail. You are generating the image at all scales simultaneously.
That is actually highly plausible. If we analyze the computational probability of this, an inverse FPN could serve as a viable, lightning-fast replacement for sequential diffusion models.
Because it skips the sequence.
The primary bottleneck with diffusion is that sequential nature. You cannot compute step 50 until you finish step 49. But an inverse FPN would allow an image to be generated across all scales simultaneously in a single, massive forward pass.
The coarse semantics dictate the global structure, ensuring the sailboat looks like a sailboat.
Meanwhile, the laterally injected noise handles the high-resolution local textures, ensuring the water looks like water. It would drastically reduce compute time while maintaining perfect global-to-local consistency.
It is taking the sheer computational efficiency of FPN and applying it to the single most expensive part of modern Gen AI. I love it.
It really brings us back full circle to the core philosophy of what Sun-Yi Lin, Peter Dollar, Ross Gershik, and the rest of the team at FAIR accomplished.
It absolutely does. And it leaves us with a final lingering thought to mull over as we wrap up this deep dive.
FPN proved that deep learning models naturally contain multiple layers of reality hidden right inside their architecture. From the raw, granular edges and pixels at the bottom to the highest, most abstract semantic concepts at the top, the network already knows everything about the image.
It just didn't know how to communicate it simultaneously.
It forces you to wonder, in our relentless modern push to make AI models bigger, deeper, and vastly more parameter-heavy, how many other free capabilities are already sitting dormant in the intermediate layers of the networks we use every single day?
What other incredible insights are just waiting for a simple, clever mathematical connection to unlock them?
It really makes you look at that sailboat photograph differently. The neural network already saw the giant sweeping sail, and it already saw the tiny orange life jacket.
It just needed the researchers to build the right pyramid to let it tell us about both. Thank you for joining us on Talk Tensors. The link to the original FAIR paper is in the description. Keep diving deep.